So I'm working on a small hobbyist type scope. Here's a typical display. I'm going to talk about this display and the software capabilities a little bit more in a different aspect of this design review. This design review is going to focus on the hardware to support this. So I'm working on a hobbyist type digital oscilloscope, primarily intended, I guess, for me, but also for my grandkids. One of them's gotten some interest in electronics, so I thought this would be kind of a fun little project that they can have access to, including the software, and could always customize it to do something different if they so chose. So I thought this part we would review the schematic. Basically, we have the micro computer board here, which is just an amazingly capable system for almost no money. It's just amazing to me. It's a black pill, uses an STM microelectronics STM32 F411. It's got A to D converter. I think it runs up to as fast as like 3 megahertz for a single channel. I'm using it dual channel, and I'm converting it about 1.2 megahertz per channel each. So, total of 2.4 mega samples per second, split among those two channels. In addition, they have the ability to inject another measurement every now and then, which I do, to measure the battery voltage. So that's happening as well. This processor or computer, I guess, actually has 128 kbytes of RAM, and I'll probably use the vast majority of that. I'm at about 3/4 of it right now, and I got some plans to do some more stuff, and that'll probably get me close to that number. And then flash, it's got 512 kbyte. That I'm not any coming close. So I'm probably at maybe 30 or 40%, and what I'm going to add won't add that much. It runs at 100 megahertz, so it's very fast, pretty amazing. Relatively low power. This whole system is designed to run off from three AA nickel metal hydride batteries. When it's running with a display at full brightness, and the display brightness matters, it is a material part of the current draw. But at full brightness, I'm consuming about 70 milliamps. And then when I go to a really dim screensaver type mode, it's more like I think 45 milliamps or something. And there's other things I could do to actually drop that current, which I'm not doing at the moment. But so uh, operationally, it should run at least 10, maybe 12 hours off from a single charge on the battery, perhaps longer. I haven't really done all the actual testing of it yet. So let's dig into it just a little bit. So we have this little board that I'm buying. It comes in a 40 pin dip, kind of like what you might expect it to be. I think there's 6/10 of an inch on center. I don't remember exactly, but I think that's what it is. So pin one is VB. That's battery in. That's to keep the real-time clock and a few registers alive even when the unit's off. And I am using the clock and a couple of the registers for settings that I save. And then pin 2 is already used internally on the board, although I could use it, I'm not. It's connected to a little blue LED. 3 and 4 is connected to the real-time clock oscillator. There's another oscillator on board, which I think is a 25 megahertz oscillator. It's not brought out, but it's there, and that's what we really use to drive all this stuff. And then they internally connect pin 6 to a switch, which you can use just as a general input. And I'm not using it at the moment, but in addition, you could use it to wake up the thing if you put the processor in a sleep mode, which I am not doing that. I'm just turning the power off instead. Then we have a couple of analog inputs. That's going to be my channel A and channel B. This is a dual channel scope. This is a 12-bit A to D converter on board. Again, as I indicated, I'm running at about 1.2 mega conversions per second on each of the two channels. And then I have the third analog input I'm using to sense the battery voltage. Pin 10 is a chip select for an internal flash. They have on this little black pill board a little flash device. I think it's a 32 gigabyte flash. It's like, man, it's just amazing. No, not gig, sorry, 32 megabyte flash. My intent is that in addition to the little micro SD card slot that I'm supporting, that I would support actually a fair amount of storage on this internal flash as well. So in case for some reason the SD micro card got corrupted, that you'd be able to recover probably a day's worth of data collection of heavy use from this internal flash. I haven't done that yet, but that's my plan. And then this has a number of communication ports, of which I'm using 2 SPI ports and 1 I2C port. And I've done connection for pinout on a couple of UART and USB, but I'm not using those other than I'm connecting them to a header. SPI1, that's the serial peripheral interface. It's a fast interface. I'm using it to talk to that onboard flash, which I'm not supporting yet. But in addition, I'm using that same SPI to talk to the micro SD card. So we have a clock, master in, slave out, and master out, slave in. And I don't remember exactly. I think I'm running this clock at about 10 megahertz. For my application, I'm just periodically storing a little bit of data, primarily a waveform or a screenshot. That 10 megahertz is like instantaneous. There's just a little bit of data being stored and you just don't even notice it, the delay. For that micro SD card, there's also a chip select, which actually, interestingly enough, is used as an input output, and I'll talk about that when I'm on that page. And then there's a charger on, which is a PWM, and what this is that if you connect a USB style C connector to this, you can power the instrument from that source. In addition to that, you can charge the batteries from that source. And the strength of that charging current is dictated by this PWM signal that I'm controlling. So I can basically control the PWM and then set the battery voltage that I'm charging. And then we have a power control for the micro SD card. I'll talk about that a little bit more, but basically I can cycle the power to the SD card and reboot that SD card if I need to under the microcomputer control. And then there's a output signal here, which is a calibration PWM that typically I'm going to probably have this set up for a 1 kilohertz 50% duty factor so that you can use it to calibrate your scope probes with it like you would normally on a scope. But right now, interestingly enough, for what I'm doing, I'm actually using it to generate a 100 hertz sine wave, which is what I'm using for testing purposes on a lot of my stuff. There's just this little 3-pin header for power, ground, and main power out, so that you can connect up to some external device if you so choose. Here's the second SPI port where it's just the clock and the master out, slave in, and that's being used to drive the display. The display that I got, actually, you can read back from it, but I'm not set up to do that. I have no need for it. The display does not support the concept of 2 images where you can like build one image in the background and then flip it at the last second, and then build another image in the background and flip it back. It doesn't support that. So I have to do all that under software control. So I don't see much reason for me to read it back. I am a little bit I/O limited here. I have more need for I/O than what I had available, so I have a little I/O expansion module. It's a 16-bit general purpose I/O, and I talk to it via I2C interface. And so that's this I2C right here, this I2C1 data and clock. That's what I use to talk to the I/O expansion module. And one of the things I'm using the I/O expansion modules is to monitor the keyboard inputs. but I don't want to have to pull for those keyboard inputs. And fortunately, that device has the ability to generate an interrupt request when one of those input changes. So that's what this line is, that this interrupt here. So when I see that interrupt, I go out and then read the keyboard status. Power on and power off. I can turn the power, once the power's on, I can turn it off under the computer control. But in addition to that, the way it powers up is via a button that you press, and then the processor boots up, and then it tells the latching relay to turn on so you don't have to hold the button anymore. I'll talk about that more in a bit when we get to that page. When you connect up the USB power source to the unit, I can sense whether that power exists or not via this logic input. And then these next four lines are just brought out on headers. They're not actually being used. They're UART, TX and RX, and the USB, DP, and DM. Those are just being brought out on a couple of headers, and they're not connected to anything more than that, and I'm not doing anything with them. Then the next couple lines are display data versus command. So when you send data to the display, when you send information to the display, there's commands, and then there's data. And then there's a reset line that I can reset the display. And then there's a chip select for the display. And then there is a backlight control for the display. And again, that backlight control I've set up as a PWM. As I indicated previously, that the backlight is a material part of the power consumption. Probably 25%, if not more, of the power consumption. And then finally, I skipped over this. This is a trigger input output. So I'm not doing much with it yet, but I have plans to do stuff. This trigger can be either an input, in which case it would trigger the data collection on channels A/B, or if I'm triggering off from channel A and B, then I can generate a trigger out, which can then fire some other device externally, or another one of these scopes for that matter. So there's four more sheets to this. There's actually five, but the fifth isn't very important. And these deal with keyboard, battery temperature monitoring, a couple of relays, and an I/O expansion module. Again, that I/O expansion module, we communicate to it through this I2C, and it generates an interrupt output request. And these relays are latching relays, so they really don't consume power except for when you're actually switching them from one position to another. And then those relays are used to control the analog input in terms of AC versus DC, and also the amplitude range selection. And so there's a couple of lines that then go to this analog section, and the analog section has, channel A and B output, which go to the A to D on the processor. And we take this calibration signal from the processor, and then we make that available on a loop of wire for testing purposes, and then we have the trigger in and out. And then we have the display SD memory card interface. Again, these are through SPI, two different SPI ports. We got the control signals I already kind of talked about on all those, and I'll talk about them in more detail when we get to that page. And then finally, we have this power page where we have the voltage that goes to the VB pin, which is used to back up the real-time clock and a couple of registers. And then we have this PWM signal that goes to the charger on circuit. And then we have these power on and off pins that control a relay position. And then we have a battery voltage monitoring pin. That's a buffered. I'll talk about that in a minute. And then we have the main power, which basically you can think of as the raw battery power or the USB power. And we have this USB power source sense. So let's dig into one of these pages. Let's start with the analog section. And if we look at, first off, ranges. Now, I'm not 100% sure I'm settled on these ranges yet. I might still tweak these a bit, but basically we have a internally selectable min or max range, and then we have external scope probe with a 10x versus 1x. So on the minimum range, which is the most sensitive, on DC we got 0 to 3.3 volts DC. Then the next range would be plus or minus 5 volts. And then finally with a 10x probe turned on, 10x position, we get plus or minus 35 volts. And then AC coupled, as opposed to DC, AC coupled we get plus or minus 1 volt, plus or minus 3.3 volts, or plus or minus 33 volts. One of the things that had occurred to me, especially with grandkids, that I could just see somebody saying, "Oh, let's hook this up to 110 volts and see what happens." So I think I've got that handled. I think I can tolerate 148 volts RMS on these analog channel A or B inputs, irrespective of what range setting I'm on or whatever. Obviously, it's going to clip and whatnot, but it shouldn't cause any permanent damage. So if you look at one of these channels, obviously here's A and there's B. A comes in and we have a high voltage coupling cap, and a relay can basically short across that relay to give you DC versus the AC. And then we have another relay that can short across this 680K, and that affects the internal min versus max. And then we have these two 22K ohm resistors in series, each a quarter watt, so effectively I got a half watt resistor there. This resistor set dictates what I can tolerate in terms of that 148 volts RMS input, which is why there's not a 44K ohm resistor here. Instead, I got two 22Ks so that I get the half watt. And then I have a couple of protection diodes on each of these channel inputs so that if they are over or under voltage, they don't cause any damage from that perspective. And then a unity gain buffer amp here. And this is critical when you're converting A to D conversions at 1.2 megahertz per channel. You don't have a lot of time where they look at these things, and they need a low impedance source for that A to D converter, so you need to have the op amps in here. When the range selection, when this R23 is in the circuit, the total input impedance in terms of DC is 1 mega ohm, which matches reasonably well with a 10x probe. That's what it expects. When this 680K ohm resistor is shorted out, I don't know the exact number off the top of my head, but I think it's like 320, 340 kilo ohm input impedance, something like that. Perhaps it's a little bit on the low side, I'm not quite sure. This high pass filter, it says right here 324K. I did write that down. So on the max range it's 1 meg versus 324K. And then this high pass filter, the 3 dB point, depending on whether or not this resistor is in or not. So on the max range it's a 3 dB point of about 7 hertz. On the min range it's 26 hertz. I have no idea what a typical scope has in terms of 3 dB high pass filter. This seems okay to me, but I'm not sure. Maybe it's not. Then in terms of the trigger in and out, it's really simple. To the left is the processor. If it's an output, then it's driving that. It goes through a 100K ohm resistor and it goes to the outside world through BNC. If it's being acted as an input, then you got this 1 meg to make sure it doesn't float out there. But so that's easily overcome by another device, such as another one of these scopes, and then through this 100K ohm resistor and a couple of protection diodes. I may have to tweak these a little bit. I'm trying to keep this R19 as high as possible. Again, the purpose is in case someone hooks up to line voltage, I don't want to break things if I don't have to. This calibration signal, this is coming from the processor, would be a 1 kilohertz square wave typically. It goes out, to the outside world. This cap and jumper here is in case I want to generate a sine wave instead of a square wave, I can throw this stuff in. And for instance, I'm generating the sine wave right now, and I have this filter in, and I use it for a lot of stuff. This is not going to be as well protected against line voltage because it's only a 10k ohm resistor here. So if someone hooks it up to line voltage, they're going to, burn out this resistor. Fortunately, this resistor is at a spot where it's easily replaced if that happens. So, it shouldn't cause any damage beyond that, I don't think. So that's the analog section. So now we look at the keyboard with the battery temperature and the relays. So the heart of this page, in essence, is this device here. Again, it's one of these little modules I'm buying from the Far East. It's an I/O expansion module. I think it's based on a TI part. I talked it through I2C interface, although there's very low bandwidth requirement here. As I indicated previously, one of the things that this device is doing is monitoring 6 switches. I think it's 6. 6 switches it monitors. But if one of those switch positions change, it generates an interrupt. That's what then causes me to come out and read basically 2 bytes from this thing. And I'm done, and I got all switch positions. The other thing I'm using this I/O expansion module for is to control these relay positions. Well, most of the time, the AC versus DC couple, the range, you're just not changing those very often. So once in a while I write to it to set the relay positions. So I'm using that same I2C to talk to an AHT10, which is a high precision temperature humidity sensor. And again, it's a very simple interface, power and ground in the I2C. This, I don't remember. I think I'm monitoring the battery temperature like maybe every 10 seconds or so. So again, it's a relatively low bandwidth thing. You don't talk to it a lot. I'm a little hyper concerned about, causing some fire because I'm overcharging the battery or something. Although the charger design is such that I should never overcharge the battery. It should, it can't. It's incapable of charging that hard. That said, in case something goes wrong, I'm monitoring the temperature so I can stop the charging. I have a second little 4-pin header here for an alternate display. I haven't hooked up to it yet. The reason it's a cute little display that was given to me, so I'm going to try and hook it up. I haven't done anything with it yet. It has a slightly different pin out than what the AHT10 does, so I got to make sure I plug it into the right header. Again, I haven't done anything with that yet. Then I have the keys down here. So this is a shift key, if you will. I can press these keys at the same time and create a chord, if you will. So to do a print screen, you do the shift and then you press enter. So shift enter is a print screen. But most of the other things are just a single switch. It's like left, right, up, down, enter. Most of what I'm doing doesn't require a chord. But there is a third chord or second chord, which is if you press left arrow, right arrow, and up arrow, all 3 of those buttons at the same time, it will cause a fatal assert by design and then reboot the unit. All right, so relays. We'll just focus on this one for the moment. Very simple. You get a signal from the I/O expansion, which we can write to from the microcomputer, and basically momentarily turn on Q9, and that will energize this coil, which will reset the relay, which is basically the position it's in now. I'm showing the reset position. If you drive IOE12, again from the microcomputer, it momentarily drives this coil, which then changes it from the reset to the set position. These relays jump over to there, And so now I'm connecting these versus not, whatever. So I have 3 of those that are set up that way, and 2 of those are for channel A, AC versus DC, channel B, AC versus DC. And then this third relay is one half of that relay controls channel A range selection, and the other half controls channel B range selection. So both channels, when you pick one range versus the other, you're doing it for both channels simultaneously. Part of the reason I did that is I was running out of space on the board, and it's like, okay, fine, I'm just going to put one relay in here as opposed to having 2 separate relays. So that's why that is. I might live to regret that. I don't know. I don't think so. I think it'll be fine. I don't think there's much else that I need to talk about here other than there's a couple of spare pins, which I have brought out to a couple test points, and I've thrown these resistors here. So one of the things I should mention, I thought this was interesting, the app note for this PCF8575, that's what's on this IO expansion module. Again, I think it's a TI part. The app note talks about, like, if you're driving a LED that, which in essence I'm kind of doing. I'm driving these transistors, that this junction looks like an LED in terms of the voltage drop. They said that this IO expansion module doesn't like that voltage drop off from the supply. Thus, the input should either be at ground or it should be at VCC and no in between. When it's in between, it can draw a lot of current. So what they recommend is that if you're driving an LED, they recommend a pull-up resistor in parallel with that LED, or in my case with this junction on that transistor. So I haven't noticed this on my prototype boards because I don't have these resistors in, but I laid out my PC board to include these resistors. And I intend to populate those resistors. So on to the display and memory card. So this is the micro SD card slot, and if you've never read about micro SD cards, they're fascinating. They're a wonderful device. Any rate, super simple interface, SPI, clock, master out, slave in, master in, slave out, power, ground, and chip select. So chip select is the most interesting thing, I thought. I was struggling with this a little bit. It's like, how do I detect whether that micro SD card is there? How do I know that it's been pulled out? And I'm trying stuff under software control to, talk to the card. Is it responding, or is it not responding? And I just didn't like any of it. And going through some of the specs for the micro SD card, I'm reading about this chip select, and the card itself has a roughly 50k ohm pull-up resistor on the chip select. Under software control, you can remove that if you don't want it, but by default it's there. Well, and I'm reading about that, and they said the intent is to use it for card detect. And it's like, oh, cool. So they got a 50k ohm pull-up resistor here on the card. I added an external 500k pull-down resistor. So if the card's present, their pull-up's stronger than my pull-down, and that chip select will be high. If you remove the card, then the chip select will fall to the low state. So when the microcomputer is not actually talking to the card, it's not doing a read or write or configuration or whatever, when it's not using the card, it programs the general purpose IO that drives this chip select. It reprograms it from an output to be an input, and then it monitors that input, and it knows whether that card is physically present or not. And it really works well. It's really cool. So onto the power. VCC. My original prototyping, I had my power directly connected, as you might expect, 3.3 volts to pin 1. And some of these no-named SD cards that I bought, names that I'd never recognized before, but they were cheap. I had problems with them. Once in a while, the cards would be corrupted. I couldn't figure out why. I'd unmount the card from my target and put it in the PC, and the PC would say, it's corrupted. Whereas if it was a name brand, somebody you heard of, Kodak, HP, SanDisk, I never had problems. They always worked. And it's like, what the hell's going on? So after much head scratching, a little bit of logic probes and stuff, I finally found where the card basically was getting in this weird state. It was sitting there saying, I'm never ready. I'm waiting for it to tell me it's ready, and it's just never ready. So finally, after some investigation, I decided, all right, I'm going to just throw this transistor in here, and I change all these lines to be in a low state so I'm not driving it. I turn the power off, wait, I don't know, 50 milliseconds or so, turn the power back on, and then the card's back up and running again, and it continues. So I'm not quite sure. I don't think I'm doing anything wrong, but maybe I am. I don't know. So I got this power so I can cycle power. That's why that's there. Then we have the display. Display again is reasonably simple. As I indicated before, we're just using SPI, but in this case, master out to slave in only. We're not coming back the other direction. So we got power and ground, clock, the master out slave in, and we got a reset signal, data versus command, a chip select, and then the backlight. Again, as I mentioned, the backlight's a material amount of power consumption, so I do PWM on that backlight. So that's what this is about over here. That transistor there. For instance, the microcomputer output pin itself could not drive this. It's too heavy of a load. So you either have to connect it direct, which is nice. It's very bright, but power consumption kind of sucks. So I've got this in so I can dim that down when I want. That's it on that page. So we go to the power page, which is really the last page of any substance. Oh, this is my little prototype board. This is at a state where it's not as complete. I got a bunch of components in here now at this point, but so here's the actual black pill microcomputer board, and there's the I/O expansion board. There's a couple relays. I got 5 relays on this board, even though I'm only using 4 of them. So, at any rate, let's talk about what this is. Battery connects here. I might have mentioned it already. I don't know. We can probably run 10, 12 hours on batteries with it running full bore the entire time. Other than the display will go dim, but other than that, A to Ds are running. I'm doing time waveform collection and displaying and all that stuff, and we can run for a while. One of the Nucleo boards I have has this. It's kind of a nice feature. They got a little jumper in here where you basically can pull out a header, a little, I don't know what you call it, plug, and hook up a current meter here so you can monitor your battery current drain or charging current. And that's kind of, I thought was nice, so I included that in here as well. So this is basically battery right here. Battery comes up, goes to this relay. The default position on that relay is open. Nothing's going on other than there is another connection for battery coming up here through 2 diode drops into the microcomputer board for the battery backup signal, and that's just used to drive the real-time clock and a couple of internal registers that are maintained. So to bring the unit on, there is a 7th switch that if you press that switch, it's a momentary switch. If you press it, it's like switching that relay position, and it connects the battery up to this main power source. And now that main power source goes out and goes over to the processor. The processor boots up, and it goes, oh, I need to turn the power on. So the first thing it does is it goes out and it toggles this relay from the reset to the set position. So now in parallel with this switch, it's connecting the battery to the main power. And then, of course, the user eventually releases the push button. That happens virtually instantaneous from a user's perspective. You press that button and you let go of it immediately, and you're up and running. No issues whatsoever. The other half of that relay is used to connect our USB power source over here through a series resistor I'm not 100% sure of this value yet, but I think 10 ohms is the right number for me. The USB comes up and it goes through the other half of that relay. So when this relay's in the reset position, power is not applied to the processor, and the USB power is disconnected as quickly as possible, at its source end, if you will. Once that relay switches to the opposite position where the power is now on, the USB, whoa, wait, I grabbed the wrong line. I'm coming up here. This is the USB power. Okay, then it switches and it becomes on, and so that switched USB power source now is available here at this signal called USB power source, and that goes to the processor as a logic input to a 5-volt tolerant pin. So in essence, our USB power can be detected, the fact that it's there. So I know that it's there versus not. And once I know that it's there, I can then start to turn on this Q3 to connect the USB power to the battery through a 10 ohm resistor. So by pulse width modulating this on and off, I can control what the voltage of this battery is. So for instance, if the battery's dead, it's like 3.3, let's call it 3 volts. 3 volts, the battery's pretty dead. You plug this into the USB, and I try and turn this thing on at 100% with this 10 ohm resistor. This voltage is not going up very fast. It doesn't just instantaneously go up to 5 volts. However, if you leave it on long enough, then this eventually begins to creep up. And so once we start hitting 4.4 to 4.5 volts, then I begin to modulate this Q3 so that I don't go above 4.5 volts. So although I think it should tolerate 5 volts for an indefinite period of time, I don't want that. I'm worried about causing a fire or something. So as I indicated, I have a temperature sensor here with the battery. I've got logic in there to monitor that battery temperature. If the battery temperature starts to creep up, I can back off on this PWM. If it continues to creep up, I can turn off the PWM. If it continues to creep up, I can turn off the power, and I disconnect the USB from the rest of the system through that relay. So I have, by design, it should tolerate a lot, and then I have temperature monitoring, and I can turn it off through the PWM, and I can turn it off through the relay. So I think I'm pretty safe in terms of not overcharging these batteries. Finally, when the relay closes / switch close, we have battery power essentially at this point where my cursor is, and that goes through a resistor divider into an op amp, and then that goes to another analog input on the microcomputer where I can monitor the battery voltage. I originally thought I could monitor the battery voltage through this VB pin on the microprocessor, and there's a way to do that. The processor is designed for you to be able to measure that battery voltage for the backup. The problem is the A to D, when we're running at the rates that I'm running, they require a really low impedance source, and I tried to use this and I just had inconsistent results and it just wasn't usable. So finally I bit the bullet and said, okay, I got to add another op amp in here, and now I get reliable, repeatable results. So that's it on this page. Finally, there's one more page. This is no big deal. This is another set of switches. These are surface mount switches as opposed to through-hole switches. I don't know if I can, with my tremor and coffee consumption, whether I can manage to solder these surface mount switches on there or not, but I'm going to try. If not, well, then I'll use the through-hole. So really, the design of this thing is very simple. Maybe a couple of it's complex only in terms of the number of parts, but the heart of it is this STM32411, just an amazing part. Thinking back to my data pack days at IRD, and it's just like, wow, what we wouldn't have killed to have this type of capability. Low power, very fast, very capable device. I'm very impressed. And by the way, this was all done on this package that George recommended. And I don't know if I'm saying the name right, KiCad, KICAD. The schematic capture and PC board stuff worked really well. The only complaint I have is if you're creating new components, like I had to create a new component for this black pill thing and for the I/O expansion board and my switch and a few things. I found the component slash footprint creation was a little bit finicky. It all worked ultimately, but it just seemed a little less polished, whereas the schematic capture worked really well. Um, and if we go look at the PC board just for grins, this is I did it as a 4-layer PC board, and the inner layer is largely power and ground, and the outer 2 layers are obviously signal stuff. So um, the this board is I think 3¼ inches tall by 7¾ wide. It's going to fit in a little pencil box that I ordered. Um, and if you look at this, almost all the components are on the back side. If we look at the front side of this thing, let's see here, front silk screen. Yeah, so the front silk screen, there's the switches all in this area over here. And then there's the display connector right there. You can't see it very well. Let's see if we can turn on these pads. Back, front copper. Um, there's the connector for the display. So the display sits right here on the top. So you can't really have any components on the top in this whole block here. You can't have any components in this area except for the key switches on the top. Those are the only ones. Um, on the back side, there's a bunch of resistors that I was able to get in here, and these are through-hole leads. And so, but the back side of the display is a blank board in this area. There's a bunch of other components here and here, but not in that area. So I was able to double up and get some of those in there. The analog stuff is all up in here. And here's the processor. And if we look at, I think it's on the power line. Yeah, nope, on the ground layer. Here's my analog, like channel A comes in here and channel B comes in here, and it's down in the ground plane buried. So hopefully it's pretty well isolated noise-wise from everything else. And then if you look at the back side of the board, we can flip that over and look at back silk screen. You can see the components are all sitting here on the back side of the board. Oh yeah, and there's a battery keep out area too. I forgot to mention that. So if we go back to the normal and flip it back over, so we got our switches right here, and the battery sits right here is where the battery pack sits. So there's a big keep out area on the back side for the battery. Big keep out area here on the back side for the display, except for a few things. So I had a hard time fitting that fourth relay in here for the amplitude range, so that's why I got dropped. All right. So here's what my present prototype looks like. This design review isn't very timely in the sense that I've already ordered the PC board layout, and I should have had the review before I ordered it. I just hadn't thought about it. So at any rate, any comments that you have would be most welcome, and I appreciate your time. Thanks.